Hello everyone, and welcome back. Today we're going to continue our exploration of single variable calculus and revisit how to calculate limits of algebraic functions. Before we introduced limits, we didn't really have any derivative tools at our disposal. Now that we know a little bit about differentiation and several of the rules that apply to it, now we're going to introduce two theorems known as the LHpitals Rule and Stirling's Formula that actually give us more algebraic flexibility when it comes to evaluating limits, provided that we can take the derivative of particular elementary functions. So the first theorem, known as the L'Hopital's rule, starts off by saying the following. Let us suppose that f and g are both differentiable functions with a particular number in both of their domains. Let's also assume that the limit as x approaches a for f and the limit as x approaches a for g are both equal to 0. They can both be right-hand limits, left-hand limits, or two-sided limits. Depends on the context. Then, if we evaluate the limit as x approaches a of f of x over g of x, which, if we take that predecessor assumption, that would go to 0 over 0, for example, then, well, what can we say about what 0 over 0 is? Well, it's not equal to 0, it's not equal to infinity, it could be equal to 5, it could be equal to 10, it could be equal to many things, right? But since we do not know what 0 over 0 is, since it's typically left as undefined, we can actually evaluate a different limit, in particular the limit as x approaches a, of the derivative of f divided by the derivative of g. Right? So keep in mind that's not a quotient rule for derivatives, it's just the derivative of the top and the derivative of the bottom. So what L'Hopital's rule says is, even though we have two completely different functions, the first of them going to 0 over 0, the second limit actually will always have the same exact limit. So hopefully that second limit expression goes to something that we can actually work with, for example 5, 3 divided by 0, or if we get 0 over 0 again, we can just apply L'Hopital's rule again, provided that the top and bottom are again differentiable functions. Let's illustrate L'Hopital's rule with a very basic example to sort of get this ball rolling. So let's assume that we have the limit as x approaches 3 of x squared minus 9 divided by x minus 3. So if we try to substitute 3 for the top and bottom, you should see that 3 squared minus 9 is equal to 0, and 3 minus 3 is equal to 0, and we get this 0 over 0 expression. Therefore, L'Hopital's rule can be applied. Now, you probably already know how to evaluate this limit via factoring, which you probably did back when we first introduced limits. But now we have L'Hopital's rule, and the derivative of x squared minus 9 and the derivative of x minus 3 are sort of independent from each other, so we can just apply that rule directly. So, since 0 divided by 0 does not give us any meaningful information, L'Hopital's rule says, well, we can find the limit as x approaches 3 of the derivative of the top divided by the derivative of the bottom. And that's going to give us an equivalent limit. So that's going to come out to the limit as x approaches 3 of 2x divided by 1. And that's actually just equal to the limit as x approaches 3 of 2x. And we know that 2x is an everywhere continuous function, so we can actually substitute x for 3 into this expression to get 2 times 3, which is just going to be equal to 6, which is the same exact answer that you would get if you were to apply, for example, factoring to this limit. And in case you're curious, if you don't remember how to do that, that's just the limit as x approaches 3 of x plus 3 divided by x minus 3 over x minus 3, and this x minus 3 issue cancels, meaning 3 is a removable discontinuity for the individual function, and that's then going to give us the limit as x approaches 3 of x plus 3, which is 3 plus 3, which is equal to 6. Now, again, note that in some sense the original function practically behaves like x plus 3 without the whole in its domain, and 2x is a completely different linear function, but they just happen to have the same exact limit. So L'Hopital's rule in some sense gives you a guaranteed way of finding a hopefully easier function that has the same exact limit as your original problem, right? Which is actually quite useful. So let's just make a quick note here about what this says. So if the limit as x approaches some point of f of x over g of x gives us 0 over 0, then the limit as x approaches a of the reciprocal of 1 over f of x divided by the reciprocal of 1 over g of x, that's going to turn into 1 divided by 0 all over 1 divided by 0. And depending on how we're approaching that from the left or the right, that's going to be equal to plus or minus infinity over plus or minus infinity. So one can formally argue that, okay, well, if we can apply LHpitals Rule to the 0 over 0 case, then technically we can also apply the LHpitals Rule to the infinity over infinity case. Both plus or minus will do, right? So if you evaluate the limit and you get infinity over infinity, you can also apply LHpitals Rule there, get a similar function that has the same exact limit, and then evaluate from there. So let's actually look at an example for that. So let's assume we have the limit as x approaches infinity of 3x squared divided by e to the power x squared. So we know that 3x squared is a quadratic function, which always increases, so that definitely goes to infinity. And e to the x squared definitely goes to the infinity quadratically exponentially fast, right? So that's infinity over a potentially larger infinity, but let's not talk about infinity comparisons quite yet. So this is definitely an infinity over infinity case. That is a really big number over a really big number. So we should be able to apply L'Hopital's rule in this case. So this is going to be equal to the derivative of 3x squared divided by the derivative of e to the power of x squared, right? So the derivative of the top, that's actually just a simple power rule. So we have the limit as x approaches infinity of 6x. And on the bottom, we're going to have a chain rule. So we have the derivative of e to the x squared, which is e to the x squared times the derivative of that interior, which is going to be equal to 2x. Now from here, we can cancel out those x's, i.e. 0 is a removable discontinuity for that function, and then we're going to have the limit as x goes to infinity of 6 divided by 2e to the x squared. We could cancel out that 6 and that 2 and make that a 3 on top, but actually we don't need to, because notice that as x gets close to infinity, the top stays at 6 and the bottom gets very, very small. So in some sense, this function looks similar to the 1 over x function, right? The top stays constant and the bottom just grows and grows and grows, and we know that that goes to 0, and then one can argue similarly that this is also going to be 0 as well, right? So there's two different cases where you can use L'Hopital's rule. Now let's actually look at a very interesting case that you may encounter when you're playing with limits. In particular, let's assume that we have the limit as x goes to infinity of 2 to the x divided by 3 to the x, right? So this is obviously going to be equal to an infinity over infinity case, so we can apply L'Hopital's rule in this particular scenario. So that's going to be equal to the limit as x goes to infinity of the derivative of 2 to the x and the derivative of 3 to the x. So that's going to come out to the limit as x goes to infinity of 2 to the x times the natural log of 2 and 3 to the x times the natural log of 3. Natural log of 2 and natural log of 3 are constants, so I can factor both of them out of the top and bottom respectively. And that's going to give us the natural log of 2 all over the natural log of 3 times the limit as x goes to infinity of 2 to the x over 3 to the x. Now, if you take a step back and realize what we have here is we have the same exact answer both here and here, and obviously we could apply L'Hopital's rule in that particular case because that's infinity over infinity, but notice that that's going to create a cyclic argument, which will not get us anywhere. Now, does this limit exist, first off? So this is one question we need to answer. Does it even exist? Now, notice when I ask this question, I'm not asking what is it equal to. I'm just asking, is it a finite number? Right? So if we look at the function f of x is equal to 2 to the x over 3 to the x, which can also be represented as 2 over 3 to the power of x, notice that that is an exponential function that is always decaying, because when x is equal to 0, it's equal to 1, and it goes lower and lower and lower. So this function is monotonically decreasing, i.e. always decreasing, and it's bounded below. Because notice that this is always a positive number, therefore 0 is a lower bound for that particular function. And one can show that if you have a function that is bounded to below and it's monotonically decreasing, then the limit of that particular function exists, right? So we can take that as fact here and say, okay, well, if it exists, let's give it a name. For example, let's assume that this limit is equal to, say, L, right? So if that's equal to L, then that means that is also equal to L as well. So if we sort of zoom out what we have here so far, so we have that L is going to be equal to the natural log of 2 over the natural log of 3 times that same value L. Right. Now I'm going to rewrite this natural log 2 over natural log of 3 using the change of base formula. I'm just going to write that as L is equal to the log base 3 of 2 times L, and I'm going to move all my L's to the same side. So I'm going to have L minus log base 3 of 2 times L is equal to 0. And then I'm going to factor out my L, so I'm going to have L times 1 minus log base 3 of 2 is equal to 0. So we have a product of two things. So we know that that is not equal to 0, which means that this must be equal to 0. So that means L is equal to 0, implying that the limit as x approaches infinity of 2 over 3 to the power of x also equals 0 as well. Using this argument, you can actually prove a more general result, in particular the limit as x approaches infinity of a to the power of x is equal to 0, provided that a belongs to the open interval 0 to 1. And that's a nice little exercise to prove, just in case you're curious or interested. Now, for these previous examples, notice that we've been working with either the 0 divided by 0 or infinity over infinity case. And this, and it's very important to take note of this, is that the LHpitals rule can only be applied to limits that result in either this or that form, right? So if you have a limit that results in something else, for example, the limit as x approaches 0 of x squared plus 3 divided by x squared plus 7x plus 7, for example, you cannot apply L'Hopital's rule to this, because when you plug in 0, you do not get 0 over 0 or infinity over infinity, you get 3 divided by 7, which is neither of those. So you cannot just apply L'Hopital's rule to everything. Moreover, you can only apply L'Hopital's rule to either 0 over 0 or infinity over infinity form. And these two forms is what we refer to as indeterminate forms. So 0 over 0 and infinity over infinity, right? So these are actually what we call the primary indeterminate forms. And there's actually other indeterminate forms called secondary indeterminate forms. And I'm just going to list these out and we'll briefly talk about them momentarily. So the secondary indeterminate forms are 0 times infinity, infinity minus infinity, 0 to the 0, 1 to the infinity, and infinity to the 0, right? So 1, 2, 3, 4, and 5 secondary indeterminate forms, and 2 primary indeterminate forms. Now, why do we call these indeterminate forms? So keep in mind, we're talking about the limits that result into these particular expressions. So 0 times infinity is not equal to 0. Infinity minus infinity is not equal to 0. 0 to the 0 is not equal to 1. 1 to the infinity is not equal to 1. And infinity to the 0 is not equal to 1. They could literally come out to any different types of expressions. That's why we call them indeterminate forms when they result from limits. So, if we can only apply L'Hopital's rule to the primary indeterminate forms, then what do we do when we get indeterminate forms that are secondary? Well, there is a nice theorem, which we're not going to prove, that if you have a secondary indeterminate form, you can always perform algebraic manipulation to represent those 5 into the primary 2, and then use L'Hopital's rule to manipulate if necessary. So let me just illustrate this with a nice little example. Actually, we'll do 2 just for fun. So let's assume that we have the limit as x approaches 1 of 2x divided by x squared minus 1 minus 3x divided by the natural log of x, right? And we're interested in this. So if we try to substitute 1 directly into the first and second term of this expression, we're going to have 2 divided by 0 minus 3 divided by, and natural log of 1 is going to be 0. So that's equal to infinity minus infinity. It could also be negative infinity minus infinity, or infinity plus infinity, or, well, it can't be that actually, because it's something minus something else, right? So in this case, we have a secondary indeterminate form. So this could literally come out to be anything. So what we need to do is transform this into either a 0 over 0 or infinity over infinity indeterminate form, and then apply LHpitals Rule. So notice that we have two fractions in this expression, so a natural thing that we could do is put them into one fraction by getting a least common denominator. So what we can do is we can multiply the left one by natural log of x top and bottom, and the right one by x squared minus 1 top and bottom. So that's going to give us 2x times the natural log of x minus 3x times x squared minus 1 all over x squared minus 1 times the natural log of x, right? So that's what we get when we get that common denominator. So let's try and substitute 1 to this expression. So we're going to have 2 times 1, which is 2, times natural log of 1, which is going to be 0. So we're going to have 0 minus 3 times 0, that's going to be 0, all over 0 times, and that's going to be 0. So that's going to be 0 over 0, which is a primary indeterminate form. So we can apply L'Hopital's rule directly to this expression, which is great. So let's go ahead and do that. So we're going to do the limit as x approaches 1 of the derivative of the top. So we're going to do 2x natural log of x. So that's going to be a product rule. And then we're going to have minus 3x. Let's do a product rule for this as well. You could expand that, but I'm just going to product rule that. And you could also expand this, but you'll still have a product rule in some sense to deal with. So let's just do the derivative of x squared minus 1 and the natural log of x. Right? So 2 product rules, not too bad. So that's going to come out to the limit as x approaches 1 of, so let's do the first times the derivative of the second plus the second times the derivative of the first. So that's that first term. And then let's focus on the next term. So minus, so it's the first times the derivative of the second. Now I'm putting brackets just to be safe there because we have that minus sign in the front. So first derivative of the second plus the second times the derivative of the first, right? And let's focus on the bottom. So it's going to be the first times the derivative of the second plus the second times the derivative of the first. Right? And that gives us that particular expression. So we can clean this up a bit, and it's actually not too scary. So it's going to come out to the limit as x approaches 1. So that's going to just simplify it to just 2, and then we have plus 2 natural log of x there. And then over here we have minus 6x squared, and then we have a minus 3x squared plus 3. All right, let's see here. Let's just make sure my signs are correct. Let's see here. Yep, everything seems to be okay there. And on the bottom, let's see what we have. So we have x squared minus 1 times 1 minus x. We could simplify this. Let's do x minus 1 over x plus 2x times natural log of x. Not much else we can do there. Okay, cool. So let's try and plug in 1 into this expression and see what we get. So that's going to go to 2 plus natural log of 1 is going to be 0 minus 0 minus 0 plus 3 all over 1 minus 1 plus 2 times 0. So on the top we're going to have 2 plus 3, which is going to be equal to 5. All over 1 minus 1 is 0 plus 0, which is 0. Right? Keep in mind that 5 divided by 0 is not indeterminate form, therefore we cannot apply L'Hopital's rule here. But keep in mind 5 divided by 0 is the circumstance that often comes up when you're dealing with infinite discontinuities, right? So therefore this limit does not exist. So our infinity minus infinity that we started with does not exist in this particular case, right? So sometimes you can guess, or actually I don't even recommend you guessing, but you can always algebraically manipulate them into a LHpitals Rule form and then proceed with the algebra from there. Let's do another example of this limit problem. So if we try to plug in 0 into this expression, we're going to have the natural log of the absolute value of 0. And in case you don't know what the natural log of the absolute value of x looks like, that's going to be this particular function. So as x gets close to 0 from the left or right, it definitely gets closer to minus infinity. So what we have here is a minus infinity to the power of 0. Right, so that negative is not going to be a concern because once we algebraically manipulate this into a primary indeterminate form, that negative is going to be chilling on the outside, so we can just apply the L'Hopital's rule form to whatever resulting indeterminate form that we get in the end, right? So this is going to be equal to something. Let's go through the algebra and see if we can work this out. So every time you have something in the form of like infinity to the 0, 0 to the n0, 1 to the infinity, those secondary indeterminate forms with exponentials, doing tricks with exponentials and logarithms is typically a good place to start in case you're not sure how to approach it. So what I'm going to do is I'm going to begin by doing the limit as x approaches 0, and then I'm going to natural log that expression. So I'm going to have the natural log of the absolute value of x all raised to the power of x, and I'm going to bring that x down in front of that natural log. And in case you're not sure why this works, and natural log cancel each other out, so you're just left with the function that we started with. So that's going to give us what? So that's going to give us the limit as x approaches 0 of e to the x times the natural log of the absolute value of x. So that's our function that we have here. So if we try to plug in 0 into this expression, we're going to have 0 times, so the natural log of 0 is going to be minus infinity, and the natural log of infinity is going to be infinity, or minus infinity, depending on how you look at it. And that's a secondary indeterminate form as well. Therefore, we should be able to algebraically manipulate that exponent into something that is hopefully equal to a primary indeterminate form. So every time you have a 0 times infinity term, what you can usually do is reciprocate one or both of these expressions. The infinity will turn to 0, or the 0 will turn to infinity, depending on which one is algebraically nicer to deal with. Keep in mind, we're aiming for a primary indeterminate form, which means whatever's on the top and whatever's on the bottom, we need to differentiate. So always use discretion when you're starting to choose the direction when you actually have choices to go with. So what I'm going to do is I'm going to reciprocate my x into 1 over x on the bottom of the top fraction. So that's going to give me the limit as x approaches 0 of e to the power natural log of the absolute value of x over 1 over x. And that is the exponent of e. So what I have here on the top, I'm going to have the natural log of 0 is going to be equal to minus infinity, and the natural log of infinity is going to be infinity, and 1 divided by 0 also equal to infinity, and that is a primary indeterminate form. Right? So that's wonderful. So I can take the derivative of the top, take the derivative of the bottom, and hopefully that gives me something to work with. So this is going to give me what? So that's going to give me the limit as x approaches, let's go infinity, 0 of e. Let's do the derivative of the natural log of the absolute value of x, and the derivative of 1 over x, right? And that's going to come out to what? So the top is going to be a double chain rule. So that's going to be equal to the derivative of the natural log, so that's going to be equal to 1 over the natural log of the absolute value of x, and the derivative of the natural log of absolute value of x is just going to be equal to 1 over x, and that's going to be divided by the derivative of 1 over x, which is going to be equal to negative 1 over x squared, which I'm going to write as that just because it's a little bit more nicer to deal with. Right? So we can definitely simplify this a little bit because notice we have 1x on top, 2x's on the bottom there, and we can throw that remaining x on the top of that fraction. So this is going to give us, and don't forget that lonely little x there, that's going to give us, where's my e? so it's going to give me the limit as x approaches 0 of e to the minus x divided by the natural log of the absolute value of x. Right? So let's see if we can plug in something into this. So if we plug in 0, notice that we have 0 over top and infinity on the bottom. Notice that if we have nothing out of arbitrarily large amount of stuff, we still have nothing. You can also reciprocate this infinity to 0, and we're going to have 0 times 0. So we're going to have 0 in either case, depending on how you look at it. So that's going to come out to the limit. Actually, we're evaluating the limit now. So it's going to be equal to e to the minus 0, which is going to be equal to 1. So that's the value of that particular limit. Before we get into the last couple things that I want to mention today, I just want to introduce these 4 exercises that I definitely strongly encourage you to try on your own, and you can use whatever tricks you want, LHpitals Rule, algebraic manipulations, whichever makes you more happy. In particular, the limit as x approaches infinity of the natural log of x over the square root of x will come out to 0. The limit as x approaches infinity of the square root of x over x will also come out to 0. The limit as x approaches infinity of x over x squared will also come out to 0, and the limit as x approaches infinity of x squared divided by e to the x will also come out to 0. So, why am I bringing up these 4 particular exercises out of the infinitely many that I could introduce? So, one can conclude for these 4 expressions, for x large enough, or if x is an arbitrarily large number, the natural log of x will always be smaller than the square root of x. We can get that from this first expression. And, so for example, if you do the natural log of 5 million, that's always going to be less than the square root of 5 million. And the square root of 5 million will always be less than 5 million. We can get that from this next expression. And 5 million always going to be less than 5 million squared. And 5 million squared is always going to be less than e to the power of 5 million. We can get that from the third expression. So we get this nice little inequality that sort of gives us what we refer to as dominated convergence of some particular elementary functions. Now, here's a question for you. Which is bigger? Which is larger? And let's assume that x is arbitrarily large as well. E to the x or x to the x, right? Now, one can think about this, well, as x gets really big, notice that the base of e to the x stays equal to e, approximately 2.71828, but here the bottom also gets arbitrarily big too, as the exponent gets big. So one can guess that as x gets arbitrarily big, x to the x will dominate e to the x, and e to the x over x to the x will get arbitrarily close to 0. But is it possible that we can prove it with the algebraic tools that we've introduced up to this point? So let's consider the limit as x approaches infinity of e to the x over x to the x, which I'm just going to call L. Right? So if I take the natural log of L, actually what I'm going to do is I'm going to call that function L. So I'm going to say L is equal to e to the x over x to the x. So I'm just going to focus on the function itself. So if I take the natural log of L, I'm going to have the natural log of this fraction, e to the x and x to the x, which I can break up into the natural log of the top minus the natural log of the bottom. That's just a property of natural logarithms in case you're curious. So then we have the natural log of L is equal to, so the natural log of e to the x, we know that's just going to be equal to x, and the natural log of x to the x by properties of natural logs is just x times the natural log of x, right? So this is what we have here. Notice that we have an x in common in this particular expression. So we have the natural log of L is equal to x times 1 minus the natural log of x, right? So if we take the limit as x goes to infinity of the natural log of L, which is in some sense a function of x, that's just going to be equal to the limit as x goes to infinity of x times 1 minus the natural log of x. And I invite you, because obviously that's going to be equal to an infinity, and then times natural log of infinity is going to be infinity, and 1 minus infinity is also plus or minus infinity. So that's going to be an infinity minus times infinity limit, but one can show using your algebraic manipulations, this is actually going to come out to minus infinity, right? So how does this sort of loop back into our original expression? So keep in mind limits can pass in and out of expressions, so we can actually write this as the natural log of the limit as x approaches infinity of L is equal to minus infinity, and then we can exponentiate both sides of this expression as so. So once we have this, then we have the limit as x approaches infinity of L, which was defined as e to the x over x to the x, is just going to be equal to the limit as x approaches infinity of e to the minus x, which is going to be equal to 0, right? And that means that as x gets arbitrarily large, x to the x will dominate e to the x. So that means that e to the x is less than x to the x for x arbitrarily large, right? So here's another question. So another question for you. Let's assume that x is a natural number, at least for the time being, and let's assume that it's also large. Which of the following is bigger? Which is bigger? E to the x to the x, or x factorial? We know x factorials grow really, really big. So where does it fit into this story? Does it grow faster than e to the x? Does it grow faster than x to the x? Or is x factorial sort of in the middle of e to the x and x to the x? This is where the last theorem that I want to introduce today sort of enters the narrative, and this is called Stirling's formula. So Stirling's formula. And it gives us a nice way of expressing the limit of expressions that contain factorial expressions. And it says the following: the limit as x goes to infinity of x factorial is equal to the limit as x goes to infinity of another function. So it sort of does the same trick that LHpitals Rule does. It says that two functions will have the same exact limit even though those functions are not equal to each other. And the function that x factorial gets close to is the square root of 2 pi x all under the radical times x divided by e all to the power of x. So these two functions will have the same exact limit, and that is the Stirling's formula. So with Stirling's formula, we're going to use it to sort of see where x factorial fits into this narrative of comparisons. So let's consider the limit as x goes to infinity of e to the x over x factorial. So if this limit is equal to 0, then we can justify that x factorial grows faster than e to the x, but it's still up to debate whether it grows slower or faster than x to the x, because we know x to the x dominates e to the x. So using Stirling's formula, this is going to be equal to the limit as x goes to infinity of e to the x over the square root of 2 pi x, and then we're going to have x to the x over e to the x, right? Notice that we have some e to the x that are equal to each other, so we have e to the 2x on top. So we're going to have this is equal to, and I'm going to factor out that square root of 2 pi also. So we're going to have the limit as x goes to infinity of e to the 2x all over the square root of x times x to the power of x, right? So here we have this expression. So now I want to ask you, which grows faster, x to the x or e to the 2x? Well, we already know that x to the x grows faster than e to the x. Well, does it grow faster than e to the 2x? You should be able to justify to yourself both intuitively and algebraically that the answer to that is yes. And even if that's not the case, it has the square root of x on the bottom helping it out also, which grows fast. Therefore, the bottom will eventually dominate the top if x is arbitrarily large, which it is. So that means this is going to be equal to 1 over the square root of 2 pi times 0, which we know is going to be equal to 0. That means if x is arbitrarily large, then e to the x will be less than x factorial. But we still do not know where x to the x lies. For example, should x to the x be here, or should x to the x be here, right? Which one, right? So we can compare e to the x and we can compare x to the x and x factorial directly and sort of see which one dominates directly, and then the story is complete. So let's do the limit as x goes to infinity. Maybe pause this video and guess which grows faster, factorials or x to the x, i.e. tetrations. So let's put x to the x on bottom, because let's assume you believe that x to the x grows faster than x factorial, which means you're hoping that this limit is equal to 0. So using Stirling's formula, we can replace the top with the square root of 2 pi x times x to the x over e to the x, and on the bottom we have x to the x. Notice that we have a x to the x on top and bottom, so we can eliminate them directly. So this is going to be equal to the limit as x goes to infinity of the square root of 2 pi x all over e to the x, and we already know that exponential functions will dominate square root functions, so this limit is indeed equal to 0. So from there, we can say that for large x, we have that e to the x is less than x factorial is less than x to the x, which completes that story. So these are two rules, the LHpitals Rule and the Stirling's Formula, that can help you analyze a lot of limits with all of our tricks from calculus underneath this. I hope you enjoyed this video, and I'll see you in the next one. Take care.